Okay, greetings. Hello, Mr. Nelson here. What up? The last time I tried filming this video, my phone died, so here we go again. Last time we were talking about prime factorization, and that's kind of leading us into radicals and the laws that govern them. What is a radical, you ask? Well, I'm glad you asked that. A radical is any root. So we could do square roots. In a square root, there's an invisible 2 that lives right there. We can have cube roots. We can have quad roots. Use different numbers in there. We can have pentaroots, right? So the pentaroot, for example, of 32 would be equal to 2, because I'm pretty sure that 2 to the power of 5 is equal to 2 times 2 times 2, 8 times 2, 16 times 2, 32. Okay, so that's just what a pentaroot is, 2 to the power of 5, or the reverse. So in order to work with radicals, let me tuck my shirt in here, I get bothered by untucked shirts. In order to work with radicals, we need to know the radical laws, the laws that govern radicals. And really there's 3 main radical laws that we're going to explore, and for this exercise, really just work with one. But here are the 3 radical laws. Actually, I'll put them up on the board proper. I'll put them up proper. So first law of radicals tells us that if I take the nth root, any root, of a number a times a number b, I can split that up into the nth root of a multiplied by the nth root of b. What does that look like in real life? That would look like the square root of 4 times 8 is the same as the square root of 4 times the square root of 8. Okay? Law number 2 is like the product law here, but for quotients. So the nth root of a divided by b, you guessed it, is the same as the nth root of a divided by the nth root of b, which, as an example, would look like, say, the cube root of 3/5. That's the same root as the cube root of 3 over the cube root of 5. That's what that looks like. And then we have our nested case where we have the nth root of the mth root of some number a. N can be any number, m can be any number. And that is the same as saying n times m root of a. So if I did the square root of the cube root of 8, that would be the same as saying the 6th root of a, the hexaroot of 8. Okay? But for today, we're just going to be using this first rule here, primarily. And I'm going to put that law right here just as a reference. So nth root of a times b is equal to the nth root of a times the nth root of b. Okay, so if we're dealing with radicals, if I want to, and so I guess when we're dealing with radicals, we have 2 versions of a radical. We have its entire version, or an entire radical, and then we have the mixed radical. Okay? And for today, we're going to learn how to convert between the 2. So how do we get from root 8 to 4 root 5? Because these, I believe, are the same number. Actually, 4 times 4 is 16 times 5. Yeah, these are the same number, or the same root. These would give the same answer. This is a full 4 times a root 5. So how do we do that? Well, let me show you. And this is where our prime factorization comes into play here. So I have, in this case, the square root of 80. There's an invisible 2 right there, square root of 80. So to work with that, what do? Well, I'm going to prime factorize this bad boy. So I have 2 here, 2 times 40 here. 40 times 2, 20. 40 divided by 2. 20 divided by 2 is 10 and 2, and then I get 2 and 5. 5 and 2 are both prime numbers. All the ends of my branches are prime numbers, are circled. So I can take this now, I can take this square root 80, and using my law there, I can actually split it up into, well, I don't think actually I'm using my law just yet, but I can split this up into 2 times 2 times 2 times 2 times 5. Okay, I can take this 80 and just split it up into what it is. This whole number is still sitting in the square root there. Now, because I am dealing with a square root of 2 here, I am looking for any perfect squares that live in here, live within this number, that I can pull out, that I can yank out. And so to do that, I'm looking for pairs of the same number multiplying each other, or squares. So here I have a pair of 2's, and I have a pair of 2's. So using my first law here, I'm going to split this up now, pull those out. So this becomes square root of 2 times 2 multiplied by the square root of 2 times 2 multiplied by square root of 5. Now I also know that 2 times 2 is 4, the square root of 4 is a perfect 2. So I'm going to pull that out. Same thing here, 2, that's the square root of 4 is 2, and then I can't do the square root of 5 into a clean number, so that becomes that. 2 times 2 is 4 times root 5. So this is equal to this. This is my mixed version. Okay? Now, I can go from my mixed back into my entire radical quite easily. To do that, well, I know that if I'm dealing with square, with an invisible 2 here, then in order to live inside here, 4 must be squared. So all I do is I do, okay, this is the same as 4 times 4 times 5. This 4 has to come back in, so it's 4 times 4 times 5 gives me root 80. Okay, let's do another example now. We'll do one more example with this stuff. Let's try, for example, square root of 45. Okay? There's an invisible 2 there. So, in order to turn this one into a mixed radical, I do the same thing. Okay, 45 divided by 2? No. Divided by 3? Yes. 3 and 15. 15 divided by 2? No. Divided by 3? Yes. And I get 3 and 5. A little bit shorter of a process. And these are all prime factors. So then I say, okay, this 2, the square root of 45, can be written also as a sum of its products, or a product of its prime factors. 3 times 3 times 5. Now, because it's a square root, there's a 2 there, I'm looking for pairs, or for perfect squares that live in here. And there is one, the only one. So what I do is I split that off. I go 3 times 3 multiplied by square root of 5, whatever's left. 3 times 3 is 9, it's a perfect square, it's 3. And then I have 3 times 5, or 3 root 5. That's not a cube root, that's a 3 in front. Let me properly write that. 3 root 5. Okay. And so, this is my mixed radical. And this can, again, go back into an entire radical by pulling the 3 back into there. And I do that because it's a square root. I do 3 times 3 times 5. And I get, again, root 45. Okay, I have a student that just walked in. What up? Okay, so the last case, or another case that we can look at is cube roots. So what happens if, or we can do quad roots, but for our purposes, we're just going to work with square and cube roots. So if I had the cube root of 81, for example, what would I do? Well, it's a similar process, but it's just a little different at the end. Instead of collecting pairs or perfect squares in the radical, we're going to be collecting cubes, or the same number multiplied by itself 3 times. But I have to start the same way here. So 81 divided by 2, no. Divided by 3, yes. I get 327. 27 divided by 2, no. Divided by 3, yes. I get 9 and 3. 9 split 3, 3. Okay? So this is a poorly written 3. So I have cube root of 81 is equal now to the cube root of 3 times 3 times 3 times 3. Okay? So and I ask, okay, because I have a 3 here, I'm looking for groups of 3 of the same number, or perfect cubes. Here we go. I have one right here. 3 out of the 4 3s makes a perfect cube. So then I split that off. I get 3 times 3 times 3 times root 3. Just using my first law there. This is a perfect cube, and the cube root of 3 times 3 times 3 is 3 times the cube root of 3. A lot of 3's there. 3 multiplied by the cube root of 3 is my mixed version of this entire radical. And then if I wanted to convert this mixed radical into an entire radical, well, this 3 tells me that this has to be cubed in order to live in this radical. So I would have to essentially go 3 to the power of 3 times 3 in here, and then this would ultimately lead me to a number of 81 cube root. Okay? That is an intro to radicals, and it kind of leads us into now working with exponents, or I guess the other half of this unit. Okay, thank you very much.